reliability analysis. And we're going to apply it to this data set, which is data on accelerated life testing of motors. There are 40 observations and there are 3 variables that are recorded. Um, so it this data, so time, the variable time describes the accelerated life test until failure. Um, and something called censoring occurs after 8,064 hours, 336 days, which means that they stop um, they stop the observation period after 336 days, and the experiment's over at that time. Okay, and this variable called censor, CENS, that indicates if the observation died during the observation period or not. Okay, um, so this is studying time until failure, um, and it also has another variable to consider, temperature. So um, running the motors at various temperatures and seeing if that affects time, for instance. That's one question that we'll address, and we'll also model time until failure. Okay, so that's the ultimate goal, is to apply this theory of reliability to this data set. So um, going through some of the theory of reliability, um, we assume that we have a density function, um, f of t, for the failures, and it considers the variable to be the time until failure. Okay. Um, what reliability means, it's a function, so what's the reliability of it lasting 1 year, 5 years, 10 years? Okay. So reliability means it didn't die. It's reliable, right? So if it didn't die, then the time until failure has to be greater than the given time t. So it could be 1 year, it could be 5 years, that lowercase t. Um, okay. Um, and this, if it's the probability that the time it lasts more than time t, lowercase t here, then that's 1 minus the cumulative by definition. The cumulative is the probability it's less than or equal to time t, and it's given by these formulas to the right. Since we're not, in most cases, we don't consider there to be a negative time, um, this integral starts typically at 0. Okay, so that's reliability. It means that it didn't fail up to time t, whether t is 1 year or 5 years. Okay, the hazard function, that represents the rate of change of the probability of failure. Okay, so uh, that rate of change means it involves a derivative. So rate of change means that there's a t plus a delta t. So the failure occurs in the time interval t to t plus delta t. Given that it survived up to time t, it wouldn't really make sense to consider the hazard um, if it's already failed. So there's a given probability, and then, or a conditional, and then we divide by delta t because that's the definition of derivative. So this first part here, that is just the definition of derivative. Okay. What I do next is I break this up into 2 pieces. The piece over here and the piece on the right. So the very first step is that I write out how we calculate a conditional probability. So this probability is no longer conditional. It's that just applying the conditional probability gives us this next inequality, and then I break it into two pieces. This first piece, that is the definition of derivative of uh, the cumulative. So this first piece can be expressed as just f of t times by uh, times by uh, this piece right here. Okay. Okay. And that piece that it takes longer than time t to failure, that is the definition of reliability right here in this denominator. So the first piece involving that limit is the density function times 1 over the reliability, because it didn't fail up to time t, so that meets the definition of reliability. So that's the hazard function, is the density function divided by the reliability. That's one way to express the hazard. Um, then if we think about the density function f of t, um, we can rewrite that in terms of the derivative of reliability, but we also need to make it the negative, because reliability is the probability of bigger than time t. So we need to do a negative sign to cancel out that aspect of reliability. Um, then you can arrive at this equation below. And if you want to prove this equation right here, you just differentiate it. The left-hand side would involve the fundamental theorem of calculus. The right-hand side involves using the chain rule and the derivative of natural logarithm. When you differentiate it, you'll get this piece above, and that's how you would prove that those two relationships are equal. Okay. If we solve for reliability in this formula, we get this equation here, and that is a classical formula for reliability. Okay, so that's all about the theory of reliability. Um, Two important concepts are hazards and reliability. And what's highlighted at the bottom here is the relationship between hazard and reliability. Okay, so a very common density function that people use to model data is the Weibull distribution. And the reason why people use the Weibull distribution is because I have a plot of it here. There's two parameters, k and lambda. Um, and people like to model data with this because um, because it can take a variety of shapes, as you can see from this density. So the density function can look somewhat like a normal distribution, one that's skewed if you look at this green or this pink curve, or it can look like something that just becomes less and less likely as time goes on. So it has a higher probability of failing earlier rather than later. If you look at kind of this orange lines, there's a lot of similar colors here, so I apologize. And similarly for some of these red and purple lines, then it looks like it can start to increase in probability later with that kind of brown curve there. So many different shapes can occur with the Weibull distribution. So that's why people like it. Okay. Um, so if we use this density function given here, we can arrive at this reliability function. And here's a few plots of that reliability function. What we focus on a little bit more than the reliability is going to be the hazard. So the corresponding hazard for the Weibull distribution is going to be given by this. And you just use the equations from the theory part. So you can use this if you know the density function and the reliability. You can form the hazard based on this theory, and the hazard for the Weibull distribution is given by this formula. Okay. One thing that we'll notice that's very important and it's shown in this graph. So if k is 1, the hazard is constant. It means that uh, any failure is due to random chance. It's not really increasing the probability as time goes on. Okay, we can see if that uh, the value of k is bigger than 1, the hazard starts to increase, meaning that it's more likely for it to fail as time goes on. Okay, um, and we see that in a lot of things. So, I mean, as time goes on, it's only, the saying is it's only a matter of time until it fails. You can think of a water heater, like the average life I was told is like 7 years, and beyond that, right, the hazard just starts to increase. Okay, um, so um, that's an instance, uh, somewhat of an instance of having an increasing hazard. Then if the parameter k is less than 1, like zero point 0.5, it follows this blue hazard curve, for example, and the hazard starts to decrease. So that's a quality of a well-built product. It's more likely to fail early, when it's just installed or starts to work. But then once things are set up, it continues to run smoothly, and the chances of failing start to decrease. The hazard starts to decrease, I should say more specifically. Okay, so these are three characteristics. So the shape parameter here, given by k, is very important, and later on we'll change the name of k to be rho. Okay, so if we want to fit our Weibull model to our data, we can do that with this Weibull fitter in Python from Lifelines. And it will produce the parameter lambda for us as well as the parameter k. Okay, and then two things of interest here is it gives us a confidence interval, a range of values that might be reasonable for lambda as well as rho. Okay, so one thing that is very interesting here is that according to this confidence interval, this value of rho, which plays the value of k above, it could be 1. 1 lies within the interval, so it could be 1. It's estimated to be 0.78 though. So it's possible um, that the chance of failure, you know, is less than 1, and the hazard decreases over time. It's also possible it's flat, and it's also possible it increases according to this 95% confidence interval. So that's not great. It would be better to have a definitive value for rho, and it would be better if this interval was strictly less than 1 or strictly greater than 1. Okay? And that's the ideal. Okay, but here, um, here that's what we have. Okay. So here's a plot of this hazard function, and we can see, of the reliability function, and we can see that, the reliability as time goes on, it starts to decrease, okay, but kind of slowly, okay. So this is the histogram of the failure times. You make a histogram of the variable time, and one thing that we can see is that doesn't look like it exactly fits a Weibull distribution. So here we have a lot of failures in the beginning, but then it starts to increase after a certain time t. Um, the probability starts to increase of the failures. So it doesn't look like the Weibull, despite its tremendous flexibility, doesn't seem to perfectly model this data. Um, there are some other density functions, FFT, that might be a little bit of a better choice, but we won't talk about that here. Okay. One thing that's considered the numerical estimate of the failure time is called this Kaplan-Meier survival curve, and it produces this survival curve. It is a stepwise function as shown in the graph, and you can kind of compare that to this curve. So even though the histogram doesn't seem to do a great job, um, this plot does generally agree with what's considered the numerical data for the survival probability, which is called the Kaplan-Meier estimate. Okay, as I mentioned, like this histogram kind of indicates there could be more going on, that the Weibull curve is not perhaps the best model for this data, but I want to point out in our data, we also have this variable called temperature. The question is, how does temperature affect the failure time? Okay. Um, and this is a Weibull model that takes into account the variable temperature. And so we're considering the effect of temperature on failure times. And you might ask, how do we do that? We do that with a modified hazard function. So this becomes our hazard function, okay? And this is known when you use a Weibull function and modify it like this becomes a proportional hazard model. And it's proportional because of this, okay? And so that's the reason why we have the exponential of these coefficients, is so that we can make a statement about how the variable temperature affects the hazard rate, okay, affects the hazard curve. Okay, so we have our estimate for the lambda for the intercept, that's 16.32. We have it for the value of rho here, okay? Um, and again, this value of rho says there could be varying interpretations here, but one thing that doesn't change when we take into account the variable of temperature doesn't affect how the variable temperature affects hazards. This formula is always true, and we can see that the coefficient is estimated to be 0.05. When we exponentiate the coefficient, this thing becomes 0.96, meaning that a 1 unit increase in temperature uh, decreases the hazard by 4%. Okay. Um, and we can come up with these 95% confidence intervals, so it could be as low as 0.05, negative 0.05, or as high as 0.04. And if we were to exponentiate this, this would correspond to a 5% decrease, or as much as a 4% decrease. Okay. This p-value tests the hypotheses that the coefficient for beta could be 0, meaning that this whole thing gets multiplied by 1 and doesn't affect the output. This p-value being less than 5% tells us to reject that null hypothesis and conclude that the input does affect the output, but we could have also reached that same conclusion based off of the confidence intervals. Okay. Okay, now these things are all measures of fit. How good does the data fit how good does the model fit the data? These are a little bit beyond us, so we're not going to talk about those. But the key point here is that um, the key point is that this variable affects the failure time, and this is a plot of the coefficients um, against possibly being 0. 0 would indicate it doesn't affect the output. The temperature one comes close, but it turns out it does actually affect it, and so it just misses that line. Okay. So how does temperature uh, affect survival? Well, this is a graph showing us different temperatures changing the survival probability. So as the temperature starts to increase, we can see that the survival starts to decrease, eventually becoming this red curve and failing a lot quicker than the baseline, which is just the aggregated effect. Okay, so if you're at a low temperature, you're going to survive longer for your motor. But then like this green one, you're going to fail sooner than the baseline, and here the red one, that's really not a great sign for your motor. Okay, um, so this is survival. One thing I want to go back to is that this is hazard. So we would say that a 1 unit increase in temperature decreases the hazard by 4%. Okay, so just from this exponential of the coefficient, because that gets multiplied by 0.96, which is 4% less.